All right, folks, we're taking a look at day 2 of our Polygons notes. That's topic 6. Topic 6, talking about everything to do with polygons. And in the second section, the second day, we've got a bunch of charts. And you will probably recognize these charts from the notes that we just did in section 1. All right, these the top 3 quarters of this chart is exactly the same as what we just did on the day 1 notes. Okay, and we've got all of the stuff already filled out that we talked about yesterday. Well, today I want to take the ideas that we talked about yesterday and show you how we can apply them to any number of sides. Okay, so first off, the first thing that we filled in on yesterday's chart was the name of the shapes. Okay, we had a triangle for the shape with 3 sides, a quadrilateral for the polygon with 4 sides, and a pentagon when we had 5 sides. And we talked about how that penta at the front of the word means 5. Okay, well, when we talk about any just general polygon, any of them will follow the pattern. The naming will follow the pattern of a pentagon. Okay, we'll call it in general. We'll call it an n-gon. But there are names that tell you how many sides. What it tells you what that number n would be. All right. If you have 6 sides, that's called a hexagon. 7 would be a heptagon. 8 an octagon. 9 a nonagon, and 10 a decagon. All right, there are a couple of places that we see these sort of prefixes all over the place. Like an octagon has 8 sides. Well, you think about an octopus has 8 tentacles. When you any of y'all that are in chemistry and physics will recognize that a decimeter, that DEC, a decimeter is 10 centimeters, and there's 10 of those in 1 meter. Um, the other place that some of these prefixes or different versions of these prefixes pop up is in the names of the months. Way on back in the day when they first started making a standardized calendar, they only had 10 months when they first started doing that. They split it up into 10 months. And the last of them, the 7th, 8th, ninth, and 10th month, were September, October, November, and December. Now, the way we have the calendar now is that, September through December is the end of the year. So that's the 9th through 12th month. But back in the day, when they first started it, it was that was the 7, 8, 9, and 10, like that October, that octo at the front of it, or December, the DEC at the front. That was the 10th month. Now, of course, the way we have it now, what they did was they inserted July and August, named after Julius Caesar and Augustus Caesar. Like, that's how long ago this stuff was set up. It was back in the Roman Empire with all of the Caesars is what they were naming things after at the time. All right, so that's how long this sort of stuff has been in play. That's where these names have come from and how long they've been around. So in general, we'll call it the n-gon, but usually we'll have a prefix right in front of that right there that'll tell you what n is. So anytime, by the way, anytime we see n in the rest of this whole chart, the rest of all the notes that we take today, anytime you see n, that is talking about the number of sides on the shape that we're dealing with. All right. So when we talked yesterday about splitting it into triangles, what we looked at was like if you connected the corners of your shape together. All right. So like if we looked at connecting point 1 to all the other corners, well, it's already connected to 4, and it's already connected to 2. But when we connected it across like that, it split it into 2 triangles. That's where this number 2 came from. And it's the same thing on a pentagon. When we connected 1 to the other corners, well, it's already connected to number 5. It's already connected to number 2. But when we draw one across to 4 and we have one that goes across to 3, that split this shape. That split it into 3 triangles. 1, 2, 3 triangles. So that's where this number 3 came from. Well, in general, for any number of sides, the number of triangles that you can split it into is n minus 2. The number of triangles that you can split by connecting the corners is n, the number of sides, minus 2. And that fits with all of these numbers that we filled out. Okay? 3 minus 2, our n on a triangle is 3. That's the number of sides. So 3 minus 2 splits into one triangle. And it makes sense because all of the corners are already connected, so it's one single triangle. When we connect the corners on a quadrilateral, we said there was 2. Well, that fits with our 4 minus 2. A pentagon was 1, 2, 3 triangles. 5 minus 2 is those 3 triangles. Now, yesterday, what we did was to talk about the interior angles, we talked about how every single triangle always adds up to 180. So that means when we're combining all the angles of the two triangles, all we did to get this 360 was we did 180 times 2. We had 180 on every triangle. We had 180 times 2 on a quadrilateral because it was two triangles. We had 180 times 3 to get that 540 because there were 3 triangles in a pentagon. Well, if you have a larger number than that, all you're going to do is you're going to take the number that's in this column and multiply it times 180. And that's what that right there is, 180 times n minus 2. That's the general formula for any number of sides. All right, the last column we looked at was this right here. It was talking about the regular version of the shape. Okay, our keyword right there is regular, because what that means is when we talk about the regular version of a shape, all of the angles in that shape are the same size. Every single one of them is exactly the same size. And that means we are taking however many degrees are in this column and we're dividing it up evenly between all of the angles. Okay? We're taking the number from here, 180 times n minus 2, and we're dividing it by the number of angles. We're dividing it by n. Okay, that's your formula. That's how we ended up with 60 up here. Okay, when we did it up here, it was 180 divided by 3 because we know that the total is going to be 180, and it's a regular triangle, so it's being split up evenly between all 3 of them. So 180 divided by 3, that's where the 60 came from. It's the same thing for a quadrilateral. We talked about how 360 degrees is going to be the total when you add it all up. But since it's regular, all of them are going to be the same. So you can just split that up evenly. 360 divided by 4. That's where that 90 came from. And that's how we also know that a regular quadrilateral is just a square, because all the sides are the same length and all 4 angles are 90 degrees. The pentagon was the same thing. We ended up with 540 degrees in total. And if you split that up into all 5 of the angles evenly, 540 divided by 5, that's where this 108 came from. Okay? So one of your assignments in this section is going to be to fill out a chart like this, to fill out all these numbers using all number of different sides. Okay? There's a whole list of different numbers of sides, and you have to fill out this whole entire chart, all of these things with the name and the number of triangles and the sum of interior angles and the measure of each interior angle of the regular version. All right? It's not hard. You just have to apply these formulas right here. Okay? So I want to shift gears for the second part of these notes to something a little bit different. Okay, this first part was talking about all of the interior angles. This next part that we're talking about is the exterior angles of a polygon. Now, we have talked about exterior angles before. Okay, back in several units ago, we had a theorem that was about triangles. And the exterior angles theorem said that if you took the side of a triangle and then extended it out further, that this angle right here on the outside, that was your exterior angle. Okay, well, it turns out you can have an exterior angle attached to any polygon. Both of these examples right here and here are both pentagons, and we're dealing with exterior angles that are made by extending the side out further past the corner. All right, so here's the deal with exterior angles. Okay, when you look at exterior angles, um, if I took this angle here plus this angle here. Those two angles together form a linear pair. Remember your definition of a linear pair. Those two angles both have this part in common, but then this other part that they don't share, right here and right here, forms a straight line when you put them next to each other. Now, we also know that in a straight line, a straight angle is 180 degrees. What that means is that this angle right here plus this angle right here equals 180 degrees. Now, because of that linear pair setup, and because of the way the interior angles always add up to 100 to some multiple of 180, because of the setup of the interior angles and because of this linear pair relationship, the sum of the exterior angles on any polygon is always 360. Every single time, no matter what, it's always 360 degrees. So if you're talking about a regular version, okay, that's our key word again, a regular version of any of these polygons, all of the angles are the same, right? That's the definition that we gave it, is that all of the angles are the same. And so because of that, you can just take that 360 and divide it evenly into all of those angles. 360 divided by 3, that's where this number 120 comes from. Okay, the reason we know that it's going to be 120 is because they have to add up to 360, and on a regular shape, they're all the same. It's the same thing on a quadrilateral. On a regular quadrilateral, your exterior angles add up to 360, and you split that up into 4 angles, you get 90. Each exterior angle of a regular quadrilateral would be 90 degrees. On a pentagon, you take that 360 divided by 5, each exterior angle would be 72 degrees because they're all the same. Okay, so when you look at these examples right here of regular pentagons, all of these angles are all 72 degrees. Every single one of those are 72 degrees. And it's because we took that 360 and divided it evenly to all of them. All right, that formula looks like this. First off, every single time, it's always going to be 360 right there. Always, every time. Then you take your number of sides. You do 360 divided by that number. Okay, this formula, much simpler than the last ones that we looked at. But this part also is going to be part of that assignment where you fill out the worksheet. All right, so take a look at that. Don't get too mixed up in what all of these formulas look like. Okay, you can see as you go across that all these numbers are related to each other. Okay, this number right here, we started with this number and subtracted 2, and then to find this number we used that one and multiplied. Then we used this number and divided. Okay, all of these numbers going across are all related to each other, so don't get too bogged down in the formula part of it if that's going to mix you up. Just remember how we can get from one thing to the next. Okay, that's what we're all about. That's what I'm trying to teach, is not just about formulas. I'm not just trying to talk about formulas and memorizing stuff. I'm trying to make you see these relationships from one number going to the next thing. How did we get to this point? Okay, how did we decide that this was true? It's all based on previous knowledge. All right, we're trying to make some connections. That's what I'm shooting for here. Okay. Just a little bit of teaching philosophy there for you. That's all we've got for this section of notes. Y'all have a good one.